Okay, let me try to attempt to prove a central limit theorem. The central limit theorem is given an infinite amount of identical distribution, xi. They add together will become a Gaussian or normal distribution with the same with the same uh, with the same mu with the same mean and variant. So this is just pretty much the formal way to write what I just stated. You can just Google what it meant. And just to review, this is a definition of a moment generating function is the expectation of tx, where x is a random variable, t an, is a variable to be assessed at a certain time. And then we define L equals log m, where the m is a moment generating function. Just remember that we're going to use it for future. We assume the distribution function have a zero mean and a variant of 1 for the notation convenience sake. So we construct the moment generating function with all the variables here. So a sum from from 1 to n. The expectation of the sum inside of the exponential is pretty much almost like the factorial multiplication. So the multiplication of the exponential. Since they're all independent variables, then we can take the multiplication multiplication out. Since they're all the same, then it's just gonna be to the nth power. Each one of them are the same. The expectation of every variable independently are the same. Thus, this expectation of all the variables summed expectation so pretty much the moment generating function of all the variables of the new distribution function of all the variable add together is a moment generating function of a single one of it, of the single one one variable to the nth power. This can be used to make this problem easier to solve, to translate into an easier problem to solve. So we just need, essentially we have the moment generating functions to the zeroth moment is essentially e to the x squared. Then we just essentially just need we just essentially need to prove this to be true. If we take log on both sides, we'll end up having this. Then we can construct the following fractions. We'll start from here to go from the left term. Remember the LT is defined as such. So this thing will become this, and then put this into denominator and to -1. Using L'Hopital's rules, take the derivative in the as x equal to c. We we'll get we'll get this taking derivative and do another derivative again. We'll have this. We just need to know, so pretty much try to need to know what L double prime is, and this red block shows what the calculation. The first moment, so Lm equals 0, and if you expand the definition of m0, it's pretty much expectation of 1. Expectation of 1 is 1, log of 1 is 0. There we go, we have equal to 0. And we do the derivative of log m. Let's pretty much do the chain rule, log m. Then we got m prime here, and then 1 over m. Since m, which is 1, as we discussed here, then we have m prime, where m prime is a first moment. First moment is the variant. Is a mean, which is 0. We do the similar things. The derivative, a second order derivative. We first do the derivative of m prime double prime, and then we'll do the one below, m prime multiple m prime and m prime square 1 over. Then plug in m double prime, where m double prime essentially is sigma. Then we have 1 minus. So I have sigma minus mu square. And then plug this into here. We'll have t squared over 2, which is this, equals this, matching with what we want here. Thus, what we attempt to prove is correct, meaning the central limit theorem is proven.